My name is Zen, and I would be giving a brief summary of my master's thesis, which involves the design of a low-cost multi-pixel photon counting X-ray detector for high-resolution dynamic imaging applications. The most recent technology for digital radiography is the flat panel detector, which benefits from the amorphous selenium thin film transistor. FPDs are compatible to both static and dynamic X-ray imaging. Digital X-ray detectors consist of two main components: an X-ray absorption layer and a readout circuit. The first component converts X-rays to electrical charges, while the second component stores and transfers these electrical charges to the flat panel circuitry. In direct conversion, X-rays are absorbed by a photoconductive layer and converted to electrical charges, which are collected under an applied electric field right after. However, indirect conversion requires two stages of the conversion layer. First, X-rays are converted to visible photons by the scintillator layer, and then these visible photons are converted to electrical charges by an auxiliary photodetector. In both direct and indirect detection, the generated charge is collected by a solid-state readout circuit such as amorphous selenium TFT or CMOS. Direct conversion methods allow a high spatial resolution due to the application of high electric field, which allows to pull the charges towards the readout electrode, and there is a lack of light spreading, which is the opposite for indirect conversion. Today, most of the deployed imaging systems for medical diagnosis and industrial non-destructive testing are based on energy integration technology. Integrating systems accumulate the X-ray signal over a certain time interval and provide a measurement such that the weight of every photon contributing to the formation of the image is proportional to its energy. Thus, high-energy photons contribute more to the image signal than the lower-energy ones. The energy information of the X-ray energy spectrum involved in the integration process is simply lost. Photon counting systems, however, do not measure the total intensity of the incident X-ray photons, but do measure the number of individual photons with the energy above a certain threshold. The measurable flux is therefore from a single photon to several million photon or pixel or second, with a theoretically unlimited dynamic range. Amorphous selenium is one of the most highly developed photoconductors due to its technological importance in the photocopying industry. Amorphous selenium is well suited for X-ray detector fabrication because it can be easily vacuum coated over a large area. In addition, despite the lower atomic number of amorphous selenium, it allows almost full absorption of X-ray photons within the medical imaging energy range. Amorphous selenium is a highly resistive material, thus the dark current through amorphous selenium remains low under the application of a relatively high electric field. However, the main drawback of amorphous selenium is that the charge transfer properties of amorphous selenium are still far from optimal to achieve acceptable charge collection efficiency, especially under a lower electric field with a thicker layer of amorphous selenium. Therefore, these design enhancements will be considered in the design that I would be including a use of a polyimide blocking layer that permits the operation of amorphous selenium devices with high electric fields, a high field capable solid state unipolar charge sensing detector that can achieve the whole dominant charge sensing, and small pixel geometries to obtain the small pixel effect. Thank you for listening.